What are the newest research breakthroughs to terraform Mars? Recent breakthroughs in terraforming Mars have focused on using engineered nanoparticles, particularly metal nanorods, as a more feasible alternative to traditional greenhouse gas strategies. Researchers from Northwestern University, the University of Chicago, and other institutions have explored the idea of dispersing metal nanorods into Mars' atmosphere. These nanorods, similar in size to Martian dust particles, are designed to trap heat and scatter sunlight toward the planet's surface, significantly enhancing the greenhouse effect. This method could warm Mars up to 5,000 times more effectively than previous proposals relying on greenhouse gases. The research indicates that releasing these nanorods into the atmosphere could lead to noticeable warming within a few months, potentially melting subsurface ice and initiating a chain reaction that increases atmospheric pressure. This could be a critical step toward making Mars more hospitable, although the researchers emphasize that much work remains to be done before the planet could support complex life or human habitation. This innovative approach could reduce the time required for terraforming Mars from thousands of years to centuries, marking a significant leap forward in the field. However, researchers caution that this process is still in the early stages, and further studies are needed to refine the technique and assess its long-term impacts. What's the newest and best research breakthrough to stop climate change? One of the newest and most promising breakthroughs in the fight against climate change involves the use of advanced AI technologies in innovative material science. AI is now being leveraged to organize vast amounts of environmental data, making it more actionable for local climate adaptation and mitigation efforts. For example, AI is helping to downscale global climate models for local applications, which is crucial for regions with limited data, enabling better predictions and responses to climate risks like wildfires and flooding. Moreover, AI is accelerating the development of new materials essential for climate mitigation and adaptation, such as more efficient solar cells and fire-resistant materials. This acceleration is crucial given the urgent need to address climate change within a narrowing timeframe. In addition to AI, new research is exploring more holistic and socially just pathways to mitigate climate change, emphasizing the need for integrated approaches that address biodiversity loss, social injustice, and economic disparities alongside environmental goals. These innovative strategies represent a significant step forward in the global effort to combat climate change, blending cutting-edge technology with broader social and environmental considerations. For more detailed insights, you can check out the World Economic Forum and Science Daily articles on these topics. What's the best way to capture all the carbon from the atmosphere and use it for production? Capturing carbon dioxide, CO2, from the atmosphere and converting it into valuable products is an area of active research with promising developments. The best current methods involve direct air capture, DAC, combined with carbon utilization technologies. Here's how it works. Direct air capture, DAC technologies use chemical processes to capture CO2 directly from the air. Companies like Climeworks and Carbon Engineering are at the forefront of this technology. The captured CO2 is then concentrated and either stored underground or used for industrial purposes. Carbon utilization. Synthetic fuels. The captured CO2 can be combined with hydrogen, produced via electrolysis using renewable energy, to create synthetic fuels. This process converts CO2 into hydrocarbons, which can be used in place of fossil fuels, thus closing the carbon loop. Building materials. CO2 can be mineralized to produce materials like concrete, effectively locking the carbon away in a solid form. Companies like CarbonCure are already using this method to create low-carbon concrete. Chemicals and plastics. Captured CO2 can be used as a raw material in the production of chemicals and polymers. For example, Covestro uses CO2 to produce polyurethane, a component of foams, coatings, and elastomers. Biological approaches. Algae and other photosynthetic organisms can also capture CO2 and convert it into biomass, which can be used to produce biofuels, animal feed, and even bioplastics. This biological approach harnesses natural processes to sequester carbon and create valuable products. Combining DAC with carbon utilization not only reduces atmospheric CO2 levels but also transforms it into commercially valuable products, making the process economically viable. This integrated approach represents a crucial step toward achieving net zero emissions while supporting sustainable industrial practices. What's the newest research on using dust on Mars to warm up the planet? The newest research on using dust on Mars to warm the planet focuses on dispersing engineered nanoparticles, such as metal nanorods, into the Martian atmosphere. This innovative approach aims to create a greenhouse effect far more efficient than previous methods that relied on greenhouse gases like CO2. Here's how it works. Metal nanorods. Researchers propose using tiny metal particles, specifically nanorods, which are similar in size to Martian dust. These nanorods are designed to float in the Martian atmosphere, where they would scatter sunlight toward the surface and trap heat. This process could significantly enhance the greenhouse effect on Mars, warming the planet more effectively than traditional methods. Warming potential. The use of these nanorods could theoretically warm Mars up to 5,000 times more efficiently than using greenhouse gases alone. This could lead to the melting of subsurface ice, increasing atmospheric pressure, and potentially setting off a chain reaction that further warms the planet. Speed of impact. According to the research, noticeable warming effects could occur within months of deploying the nanorods, marking a significant advancement in the timeline for terraforming Mars. This approach could reduce the time required to make Mars more habitable from thousands of years to just a few centuries. This research represents a groundbreaking step toward the goal of terraforming Mars, though it is still in the early stages. Further studies are needed to refine the method and fully understand its long-term effects on the Martian environment. How to stop climate change on Earth while terraform Mars simultaneously. Simultaneously addressing climate change on Earth while terraforming Mars requires a multi-pronged strategy that leverages advanced technologies, sustainable practices, and international collaboration. Here's how both goals can be pursued together. 1. Advanced carbon capture and utilization, CCU. On Earth, invest in direct air capture, DAC, technologies to remove CO2 from the atmosphere and convert it into useful products like synthetic fuels, building materials, and chemicals. This helps mitigate climate change by reducing greenhouse gas concentrations. On Mars, utilize captured CO2 for in situ resource utilization, ISRU, to produce essential materials like oxygen, water, and methane for fuel. Mars has a CO2-rich atmosphere, so technologies developed for Earth can be adapted to produce resources needed for human habitation. 2. Renewable energy expansion. On Earth, rapidly scale up renewable energy sources, solar, wind, geothermal, to replace fossil fuels. This reduces greenhouse gas emissions and promotes sustainable development. On Mars, use solar energy as the primary power source, given Mars' relative proximity to the Sun and the need for sustainable energy for long-term colonization. Advances in solar panel efficiency and energy storage on Mars can be applied to improve Earth's renewable energy systems. 3. AI and machine learning for climate and terraforming. On Earth, AI can optimize energy grids, enhance carbon capture efficiency, predict climate patterns, and manage resources more effectively, helping to meet climate targets faster. On Mars, AI can be used to model and optimize terraforming strategies, such as the deployment of nanomaterials or the management of habitats. It can also help in automating the construction of infrastructure on Mars using local resources. 4. Sustainable agriculture. On Earth, develop and deploy precision agriculture techniques to increase food production efficiency, reduce waste, and lower emissions. Techniques like vertical farming and regenerative agriculture can restore soil health and sequester carbon. On Mars, research into closed-loop agricultural systems for Mars, such as hydroponics and aeroponics, can inform sustainable farming practices on Earth. These systems are crucial for supporting life on Mars and could revolutionize food production on Earth by reducing land and water use. 5. International collaboration and policy. On Earth, global agreements like the Paris Agreement need to be strengthened with binding commitments and financing mechanisms to reduce emissions. Collaboration between nations on technology sharing and climate adaptation strategies is essential. On Mars, international cooperation in space exploration can pool resources and expertise, accelerating the development of terraforming technologies. Collaborative efforts can ensure that Mars exploration complements Earth's climate goals, rather than diverting attention or resources from them. 6. Public engagement and education. On Earth, raising public awareness about climate change and the importance of sustainable practices is crucial. Education programs can empower individuals and communities to take action. On Mars, public interest in Mars exploration can be leveraged to inspire action on Earth's climate issues. The challenges of Mars colonization can be used as a backdrop to highlight the need for sustainable living on Earth. Conclusion: achieving these dual goals requires a synergistic approach where technologies and strategies developed for one purpose benefit the other. This integrated strategy ensures that while we look to the stars, we are also taking care of our home planet. What would be the best method to stop climate change on Earth that can be utilized to terraform Mars? The best method to stop climate change on Earth that could also be utilized for terraforming Mars is direct air capture, DAC, and carbon utilization. This approach involves capturing carbon dioxide, CO2, directly from the atmosphere and converting it into useful products or storing it permanently. Here's how it can be applied to both Earth and Mars. On Earth, direct air capture, DAC. Climate change mitigation, DAC technology involves using large-scale machines that pull CO2 directly from the atmosphere. The captured CO2 can be stored underground, carbon sequestration, or converted into products like synthetic fuels, building materials, or chemicals. This reduces the overall concentration of greenhouse gases in the atmosphere, helping to mitigate climate change. Benefits: this method directly addresses the root cause of climate change, excess atmospheric CO2, while also creating economic value through the production of usable materials. On Mars, terraforming. Atmospheric enhancement: Mars has a thin atmosphere composed mostly of CO2. DAC technologies can be adapted to capture and concentrate this CO2, which can then be used in various ways to support life and industry on Mars. For example, oxygen production: CO2 can be split into oxygen and carbon through processes like electrolysis. Oxygen is essential for human respiration and can also be used as rocket fuel. Greenhouse warming: the concentrated CO2 could be released strategically to enhance the greenhouse effect on Mars, gradually warming the planet and potentially melting polar ice caps to release water, which is crucial for supporting life. Building materials: similar to Earth, captured CO2 on Mars can be used to produce building materials, aiding in the construction of habitats and infrastructure using local resources. Synergies and advantages. Scalability: DAC technology can be scaled up to meet the needs of both planetary environments. On Earth, it can be deployed globally to address climate change. On Mars, it can be tailored to the unique atmospheric and environmental conditions. Dual benefit: the research and development of DAC on Earth can directly inform the methods and technologies used for Mars terraforming. This creates a feedback loop where advancements in one area can accelerate progress in the other. Challenges and considerations. Energy requirements: both Earth and Mars require significant energy inputs for DAC and subsequent CO2 utilization processes. On Earth, renewable energy sources like solar and wind are crucial for powering these systems sustainably. On Mars, solar power will likely be the primary energy source, though it may need to be supplemented by other forms like nuclear energy. Economic and policy support: for DAC to be effective on Earth, it needs substantial investment and supportive policies to scale up. These same technologies, once proven, can be adapted for Mars, but initial development will likely be Earth-based. In conclusion, direct air capture and carbon utilization offer a promising dual-use technology that can help mitigate climate change on Earth and serve as a key component in the terraforming of Mars. The cross-applicability of these technologies makes them an attractive focus for research and development.